Hi everyone, my name is Ali and today I'll be presenting our paper FSIOL-310, a robotic dataset and benchmark for few-shot incremental object learning to be presented at IEEE ICRA 2021. Deep learning has achieved remarkable success in object recognition tasks. However, most deep learning systems are required to be trained in a batch learning fashion. That is, they require all the training data to be available in a single batch. Now, incremental learning is a field in machine learning in which models are required to be trained using data coming in incremental steps. And the model is also supposed to remember the previous data when learning from new data. One of the reasons for deep learning success is the availability of large labeled datasets such as ImageNet and C400. But in real world applications, robots generally have very limited data with very limited supervision. So there is a field in machine learning now called few-shot learning, in which the model learns using a very small amount of label data. The few-shot incremental object learning is a combination of few-shot learning and incremental learning, in which the model learns incrementally but only using a small amount of data for each class. And this is a setting we introduced in our previous work. The few-shot incremental object learning obviously has vast robotics applications in the real world, where autonomous robots have to operate over a long period of time in any environment. However, there are very few incremental learning datasets that are captured using robots, and to our knowledge, there is no dataset that has been specifically captured for the few-shot incremental object learning problem to be tested on the robots. Creating highly accurate incremental learning systems is a challenging task because of the catastrophic forgetting problem, in which the incremental learner forgets the previously learned classes or tasks, and the overall accuracy decreases. Now, to deal with this problem, many different approaches have been taken in the past 2-3 years. Among the first are the ones that use or store the data of the old classes and use it while learning new classes, like ICARA or EIL or BIC and many more. Then there are approaches that try to avoid that by using generative memory, using GANs and autoencoders, and among those are AEC and DGM. Then there are others that try to regularize the neural network using the weights of the previously learned tasks, and among those are LWF and EWC. And finally, there are other approaches that go in a different direction using clustering techniques, and among them is a CBCL, our previously proposed approach. Now, one of the main limitations for these approaches is that they have been tested on simpler datasets like MNIST and C410, which contain idealistic images in constrained environments and not suitable for data collected by robots in real-world environments. And most of these approaches are also not designed for learning from few labeled samples because of this availability of large data sets as well. Now, there are a large number of datasets in robotics community that have been proposed for object recognition tasks. Now, among these datasets, in the first category are the ones that have been captured in a constrained turntable environment, in which a camera can be used to capture the images on a table, and a robot is not even required. Among these are Coil 100, NOR, Big Bird, ROD, and many others. But one of the issues with these datasets is that they are still captured in more idealistic environments, and also they contain very small number of objects per class. For example, the biggest dataset, ROD, only contains about 6 objects per class. Now, ARID is one of the datasets that has been captured using a mobile robot, manually controlled by a human, in more real-world environments, and it contains a lot of issues that could be faced by robots in the real-world environment. But it still contains about 3 objects per class. Now, all of these datasets have been designed for the batch learning problem, and none of them were initially designed for testing the incremental learning problem. Core 50 was actually the first dataset for the robotics community to test incremental learning. It was a great dataset that it took the initiative for testing incremental learning, but it still lacked some in different ways. For example, the objects were captured with a human holding them in its hand, so it can be a difficult problem in real-world scenarios where there is limited human supervision. And it also only contained 5 objects per class with only 10 classes. Recently, OpenLORS is another dataset that has been proposed, and it actually is captured with an autonomous robot similar to ARID, a dataset, and however, it also contains very small number of objects per class, although more number of classes, 19. Now, one of the issues with most of these datasets, and specifically the incremental learning dataset that I just said, Core 50 and OpenLORS, is that they contain same objects in the train and test set, which can be a problem because in the real world, the test objects could be quite different from the training objects. And they're also captured in very similar backgrounds, which again can be a problem in the real world scenarios. Another issue is that for the incremental benchmarks, they use the previous objects and show them again in new increments, which kind of takes away the main idea of incremental learning, where usually the robot doesn't have the data that it actually had in the previous increments. And finally, none of these data sets were actually designed for the few-shot incremental object learning problem. So in this paper, we proposed FSIOL-310 robotic dataset specifically designed for the few-shot incremental object learning problem. It contains 22 object classes with 310 objects, so 11 to 17 objects per class, which is the largest datasets currently in terms of objects per class. And it contains only 660 RGB images, just because it is captured for the few-shot incremental learning problem. So there are a small number of labeled images. And all of those images were captured using a Baxter robot on a tabletop environment. And it is suitable for class level and object level classification. And specifically, there were different objects in train and test sets. So for example, there are all these objects from the FSIOL-310 dataset, and you can see like there are different objects in the train and test set. Our dataset also captured various issues that arrive in the real world environments. For example, imperfect background, like a lot of objects are also transparent, like hair clip, and lighting conditions are not ideal, and different objects are of different sizes or are at different distance from the camera, which can be another big issue. For example, the hair clip on the top one is very small, and the glass is bigger, so there is already that difference. Now, we performed benchmark evaluations on FSIOL-310 using 8 state-of-the-art approaches. Among them, there is fine-tuning, which is just a baseline for catastrophic vetting, because the model doesn't use any specific technique to avoid the problem. And then there is the few-shot learning baseline, which is actually the best learning baseline, in which the model simply uses a feature extractor and then trains a linear layer using softmax loss. And in this case, the model gets the data of all the classes at all times. For implementation, we used PyTorch as the framework for all the models and experiments, and we performed 5-shot and 10-shot learning experiments on FSIOL-310, in which, again, for 5-shot, we have 5 training examples per class, and 10-shot, 10 training examples. And we used 2 classes per increment, so it's essentially 11 increments per 22 classes. And we report accuracy after each increment, and also an average incremental accuracy over all the increments. And we also performed all the experiments 10 times with different random seeds for robustness. So first, we performed a benchmark evaluation using a pre-trained network on the ImageNet dataset. And as you can see from the results, from left side it's 5-shot and right side 10-shot, that almost all the models perform poorly on this task on FSIOL-310. The only 2 models that actually perform fairly well were FLB and CBCL. FLB is a batch learning baseline, so it obviously will perform better than all the models. CPCL was closer to FLB, but still the final accuracy was about 8 or 9% lower. And the only reason was because CPCL was specifically designed for the few-shot incremental learning problem in our previous work. Then we tested the effect of using different base features. So we, instead of using a model pre-trained on ImageNet, we trained it on C500, which is a much smaller data set. And we saw that, again, all the models perform still poorly. However, CBCL and FLB now produce much lower accuracy because they depend on the initial features from the feature extractor. So this actually kind of shows that even the models that were designed specifically for the few-shot incremental learning problem are dependent on the feature extractor. Finally, we performed experiments using different backbone architectures. So for example, ResNet 18, VGG16, and ResNet 50, just to see the effect that it will have on the final accuracy. Again, most models did not produce good accuracy, and FLB and CBCL still produced similar accuracy as we saw before. However, we saw that using a deeper backbone architecture does help CBCL and FLB because of, I guess, better features generated by that model. So in conclusion, we have proposed the first data set for testing few-shot incremental learning on robots. FSIOL-310 covers many real-world challenges faced by robots, such as imperfect lighting, object transparency, and sizes. And we also performed benchmark evaluations using 8 different methods, which showed that few-shot incremental learning is still an unsolved problem, and most models are not suitable for this. There is a limitation for our dataset that all the objects were captured using the same background, so that can be a problem because realistically there will be different backgrounds for different objects. Finally, the future models for incremental learning can now use our dataset and benchmarks to produce models that have improved performance on robotics applications. Thank you. And if you have any questions, please let me know.